Hello everyone, I'm very excited to see you all here today. My name is Pat and I would like to present you a functional data structure, an efficient ArrayList alternative for an open source project called Javaslang. Lately I was quite involved in the open source community and I encourage you all to contribute also. You will learn a lot from all your contributions, and by learning the subject and learning a lot about yourself, you will also give back to the community and make the world a better place. You will also grow from, as I said, all the feedback, and you will receive a lot of feedback. Instead of all those certifications that prove your theoretical knowledge, open source contributions speak about your real world value. The open source library that I contributed this data structure that I will be talking about is called Javaslang. It's an object functional library, basically mimicking Scala where Java lacks. So you can say it is basically Scala in Java. It's customary in functional programming circles to start with a self-deprecating intro. So who am I to disobey that? I'm not an expert in functional programming. The other thing that people start their introduction with is their own subjective definition of what they think functional programming is. Well, here's mine. I think it's a way of communication that minimizes surprises. These so-called surprises are often called side effects. And persistent data structures, for example, the one that I will be talking about here today, achieve that by versioning. It's immutable data structures that have the same time and space complexity as their mutable counterparts. Let me do a quick intro about ArrayList, the one that this data structure replaces, basically a growable array. It has constant time get, access to any element, constant time update, you can query the size, you can append at the end, and also you can take a small part of it for free basically and pop the last element. However, the last two sublist and pop have some memory leaks that we will try to avoid. And it has other drawbacks that are worth mentioning. We've grown so accustomed to them that we might not remember. For example, they're not symmetric. An ArrayList can be used as an optimal stack. You can query and you can remove the last element, but you cannot use it as an optimal queue. While you have access to the first element, you cannot remove it in constant time or insert element into it. Our other concern is that it's a real memory hog. Whenever you try to insert primitives into it, then they are boxed, requiring additional memory. Also, the underlying array that stores all these elements is almost always bigger than the actual elements that it's storing. And this array is waiting to be filled. Also, if you remove elements from the end, for example, you want to use it as a stack, the underlying array will not be resized or something, causing also memory leaks. And if you have a sublist, which keeps a small part of the array, it can either be linearly implemented or in constant time. The biggest concern with the usage of mutable data structures is that every change that you make propagates globally. You have to really trust all your neighbors and everyone who uses that data structure to be sure that their modifications don't affect yours and vice versa. This causes, so to say, dependency explosion. Every local change becomes global and you will depend on every user of that data structure. In a way, all these modifications burn the bridge behind you. You cannot go back to that state anymore. How do people usually avoid this? Keep this locality so that you don't have to know about the whole world. Some use defensive copies. The problem with that is that it's very expensive both in time and space. Or maybe you can use an unmodifiable wrapper around arrays. That has lots of other problems in itself, but that requires a lot of discipline to use. And in case of concurrency, you have to lock everything so that only one of them change it. And the problem with locks is that they are meant to slow things down, not to speed things up. The other side effects of mutability is that since you only have a single state, you cannot restart part of an application. You cannot save a state easily and restart from there. For example, if a server crashes, you cannot say, okay, this is where it got to, we will continue from there. Therefore, hot swap is often not a possibility. What is hot swap? When you have a live code, a live working application, and you want to change a small thing in it and redeploy it, but not redeploy the whole application, not just the change. In a mutable environment, that's usually not possible. And when you're doing debugging, you can only go forward, not backwards. You don't have a time-traveling debugger, as for example in Elm. And most of these drawbacks that I presented are about all mutable data structures, not just ArrayList. how can we avoid that, or how can we circumvent this? How can we design against these for the advantages? First, let me present a real-world use case of why we would need that. I'm not a big fan of hello world examples or Fibonacci sequence examples. The problems that we are facing, those should be simplified and presented whenever we think we have a solution for a bigger problem. Let's start in this case with a very simple text editor. It will be so simple, in fact, that we will only support edits and undos. We will have a text. We will not be able to append to it, prepend, or delete for the sake of simplicity. How would we model it? Our first instinct might be to use an array list and some diffs, all the modifications stored that represent our changes. We could do that in two ways. Store the bottom, the original source, and then store all the diffs that we have made. For the reverse, we can store the top version, the latest edition, and store reverse diffs. In each case, the time travel, if for example I want to check out what this document looked like a month ago, each of these solutions requires that time traveling would be linear, not constant time. And I'm sure that many of you have seen some editors where we pressed undo too quickly and the text got all gibberish. If we would store diffs, it would be memory efficient. However, it would be quite difficult to implement. Let's see another idea quickly. In Java and in most other languages, strings are already immutable, making the versioning very easy. However, they don't have so-called structural sharing. If I change only a single paragraph, I expect the rest of the paragraphs to stay the same and stored in a single place in memory. That's usually not what happens with strings. The advantage would be that we would have direct time travel because all the states wouldn't be constructed, they would be stored. It would be easy to implement, but it would be a real memory hog. Is it possible to design a data structure that is memory efficient, is time efficient, and is easy to implement? If the answer would be no, then I wouldn't be holding this presentation. Let me try to model some random characters and store them in a string, and store the same thing in Javaslang's vector, the one that I implemented. We will make random edits. The string edit will be a substring to any given position, the lowercase of the current character, and the rest of the substring. In a vector, we will simply call an update. If we compare the two outputs, then we can see that our implementation for 1,000 elements occupies about 7 times less memory. Okay, getting back to the presentation. For now, you will have to believe me that it's faster. My goal in implementing a data structure that can achieve better results memory and time-wise than a simple immutable data structure, I've had a few goals and a few things in mind at first. I wanted to reinvent things. I knew about this data structure about as much as you know about it now. I wanted to reinvent it because I can look at it later if I don't succeed in any way. I had a lot of compromises. I needed speed-wise to be optimal, memory-wise, but also very maintainable. It turned out that a lot of times code that was a lot more optimal than other alternatives was changed to a simpler format that got slower, but it got way more easier to maintain. And I cannot stress how important this part is. I think it's a lot more important to make code readable and maintainable because it might get faster from itself. For example, Java 9 introduced some array optimizations which made this implementation even faster. However, if you don't maintain your code, it will not get better. This implementation automatically supports primitives without wrapping them, also gaining considerable memory advantage. And usability-wise, it's completely symmetric. I want you all to meet the Radix-Balanced tree. What is the Radix-Balanced tree? Clojure calls it a persistent vector, Scala calls it a bitmap trie. It's the same thing, basically. It's a very wide and shallow tree. It all contains small arrays, and the information is stored only at the leaf nodes. When we would like to access any given element in it, we only have to access as many elements as the height of the tree. In our case, that's often a base 32 logarithm of the given number. Modifications of the tree are naturally not done inline. We cannot modify, but we can create a copy of it, but not of the whole tree. Only the path from the root to the given node has to be copied. So let's see quickly how accessing a given element is done this way. First, let's talk about our decimal system. How does that work? If you have separate digits in a given base, then you can imagine them as having separate boxes that you can choose from. If we imagine 10 boxes all containing 1,000 numbers, then the 3,210th element would be in the third box. If we open the third box, we will see it contains 10 boxes again. The 210th element that remains will be in box number 2. The 10th element will be in box number 1, and the first element would be in 0. And since we left these boxes empty, cats occupied it. You can put anything in it, images, numbers. They don't contain boxes anymore. Let me present you in another way. You have 10 boxes and you want to find the 3210th element. You open box number 3. You want to find the 210th element. You open box number 2. You want to find the 10th element. You open box number 1. You want to find element with index 0, and that's an A. In this case, it's text. You can store whatever you want in the leaf nodes, obviously. What would happen if we would simplify this to a binary system? You would have 2 boxes and you want to find a 1011th element in it. Given 2 boxes, 1, 0, 1, 1. It's a Y. Every element is uniquely identified this way, and in case of a binary tree, we can also show it in a diagram shortly. Before that, let's imagine a simple exercise. We want to store all the alphabets of all the languages in the world. We want to do that by starting off from a simple alphabet, for example, the English alphabet, and adding and removing letters from it. For example, there's no W in the Hungarian alphabet. And we want to remove that and add the new ones. However, we want structural sharing. We want, for example, if in other languages start with ABC, we want them to point to the same structure. Well, let's imagine the English alphabet, and where each of the letters is put inside the single box. Now let's group them in boxes of 2. After that, let's put the results in boxes of 2, and the results in boxes of 2, etc. Basically, in this way, you can say the logarithm of base 2 means how many times can you group the results in 2 boxes. This will come in handy later. As you can see, boxes inside boxes, and each one of those is identified in a unique way. Can we increase the base number in order to not have levels so deep? Basically, a transition between a linked list and an array. What we want, a linked list would have linear access to every element, and an array would have instant access to every element. The previous diagram can also be shown as a complete tree. However, for greater bases, it's not always possible to display them in a diagram. If our base is 2 and we were storing the alphabet, what would be the index of k in this case? It would be the path that we traverse from the root. Given an index of 0 and 1 for these 2, the index of k would be 0, 1, 0, 1, 0. This is, however, too deep for only 26 elements. Can we compress it? We could compress these 2 levels and the second levels. In that case, we would get 4 boxes, not 2. And if you check out the blue nodes, you can see the number of nodes reduced dramatically. Now if we want to get to element k, you will have to traverse down index 0, index 2, index 2. So this will be the digits in base 4 that identify k uniquely. We can compress it even further with nodes of 8 values. In this case, the index will be 1 and 2, 0, 1, 2. Or in 16 nodes, or in 32 nodes where it won't even have separate levels. How do you calculate the digits that you need to traverse down the tree? If the radix is not a multiple of 2, then you will have to divide and you will have to calculate the remainder to extract every digit one by one. However, if it is a multiple of 2, then we can simply group the existing base 2 numbers, and we can only use a bit shift and an AND operator, which is among the fastest operations the CPU can handle. As you can see, base 32, which is often used for these kind of data structures, uses 5 digits of 2 to traverse down the tree. How does that look like? For obvious reasons, I cannot show this to you as a tree, but I can show it as boxes. If we're interested in elements with index 3, 1, 4 or something, then we will open box number 3. It will contain 32 elements again. We will open box number 1. It will contain 32 elements again, etc. At level 1, we can store 32 different elements, numbers, strings, objects. At the second level, given a full tree, we can store 1,000 elements. With 3 levels, we can already store 30,000 elements, and in case of the same tree that we have seen before, this one, which had 4 levels and stored only 26 elements, we can store with a base of 32 1 million elements already. But let's scale it up. We would like to store the world's population one by one. I hope the NSA is watching, as this might come in handy. What will be the width of this tree? It will be about 8 billion. What will be the height of this enormous tree? It will be about 32 base log of 8 billion, which is only 7. Let me make it clear how big this number is. You cannot store it in an integer. You cannot even index it. The index is already a long, and the height of the tree is only 7. Now the structure overhead, the part that holds these leaf nodes together, is even in this case quite small, only 3% compared to if it were stored in a single array, which obviously you cannot in Java because it would be way too big. If this tree would be made in a diagram shown with boxes of 1 square centimeter, then the height would be 7 centimeters and the width would circle the earth twice. That's why this height of the tree is usually considered a constant. In real-world cases, it's always less than 6 or 7. You will run out of memory before you will have problems of indexing this tree. So this is how you index a tree. How can you append and prepend? First, append is quite easy. This is how you create such a tree. Given an empty vector, and without loss of generality, I will use a base of 2, even though in reality, usually a base of 32 is used, as I have pointed out. An empty vector this way will consist of 2 empty boxes, arrays, positions, whichever. If you insert a single element into it, then the first one will be occupied. If you insert another one, no surprise here. However, where should we insert C? There's obviously no room there, but we can create another 2-element array upwards and link the whole left side without modification and appending another element that's in the closest vicinity to the element that we're looking at. So ABC will look like this. This will be ABCD. But we have the same problem again. Our whole data structure is full. What do we do now? The same thing, put a new root to it, point the whole data structure to the old one. This is why it's called structural sharing. And the left side, only a single element of the height of the new tree will be inserted, so 3 elements in this case. However, again, imagine, as I said previously, new heights are rarely added in the base of the tree is a lot bigger than 2. Again, we insert elements into it, and what happens when this is full? Nothing. Let me show you the same thing in base 32, just so that you understand why I didn't create the whole example. We can insert the whole alphabet, and I even started it in lowercase, and it's still only stored in a single array. After that, I finally, when I finished all the alphabet, I only got 2 slots from the 32. I would need to insert 1,000 more elements before it gets to 3 levels. So append is pretty obvious, however, prepend is a bit more complicated. In fact, so complicated that when I tried to come up with how this can be programmed, I wanted to give up and rename it to pretend, because that would at least be correct. Rich Hickey came up with this data structure in Clojure. He didn't even implement prepend, only append, so it's not symmetric in Clojure. In Scala it is. The first step is exactly the same. We have an empty vector and we insert 1 before it. Well, we can insert it here. What happens if we insert 1 before? We could move it over, but let's remember these 2 boxes represent the normal base, which is 32. Whenever I prepend, if I move everything over, that would be linear, and that's not what we want. However, we could branch upwards. And after I branch upwards, now the right part becomes the existing data structure, and B will become its closest left neighbor. You may also notice that if I would have shown you this picture before without the offset that you might not even see, then you would have said that this element has index 0, 1, which is the first element, not the 0th element. Therefore, we have to note where the first element begins, and that is stored in an offset separately. If I insert 1 more element, then this offset naturally will become 0. However, what happens if we insert 1 more element before that, a D? This whole data structure that is here will simply be referenced to, no changes there, and D will be prepended in the closest vicinity of the existing data structure, this D. And an offset will be set of 3, which points how many missing values are before the first value. This offset will be used whenever someone asks for a given index, but simply this offset will be added to that index. Therefore, this part is not even created. This can be regarded as a null node, pointing nowhere. But since every offset is shifted by this number, the client cannot access it, making it safe. If we insert E this way, it naturally occupies the box before it, and if we insert 2 more, then this phantom node will actually be created and referenced to. What happens if we branch up even more, if we try to insert 1 more element? The same thing again. We will create a path of the same height that we had before, and all of that is gathered in a new root node. What will be the offset this time? Yep, 7. So even though this isn't created, this probably is created. With an offset 7, the first element would be this. Is this tree balanced? Let me point you to the tree. So you can say that, at least for the elements that are accessible, the tree is balanced, because the nodes that you want to access are only available at the leaf nodes. These might not be balanced because they're missing. The other thing why it is balanced is because it's constructed from bottom up. Usually the binary trees that you have seen are constructed from the root downwards. Clojure and Scala implemented this in different ways. As I said, Clojure simply skipped this, but it has append. Since people want to change or access the extremes of a data structure a lot more often than the middle, for example, you want to append and prepend, but you rarely insert in the middle, Clojure and Scala introduced depth-independent so-called staging areas. For example, if you want to append elements, it stores a leaf node separately from the tree, and whenever that separate leaf node is full, only then is it inserted into a tree, therefore avoiding all the excess because of the height of the tree. Scala does something even more magical. In fact, it makes the source code very difficult to read, and I think it's a compromise that optimizes too much for speed. It extracts the last used node. Let me show you this. Whichever node was lastly used is extracted from the tree, stored separately, and if you keep updating the same leaf, then you don't even access the whole tree. However, if you append and prepend and append and prepend, or you don't want to access elements in a linear way, then this will slow things down a lot more. Let's see the next one. How do we update an element? How do we modify existing data structures? Here is the alphabet again, and we want to change capital letter T to lowercase 1. Naturally, we cannot just go there and change it because other people might be using this as the English alphabet. If I just start modifying it, then I will ruin their application. What I can do, however, is start copying the path that leads to this T. First, let's copy the root. Now I have 2 separate data structures that represent exactly the same tree. Why do I want that? Because only I know about the new one. I am allowed to modify this one node. Why would I want to modify it? Because I will go along the way, copy the path, and assign the new array to it. Go further, copy the new, assign it to the parent. Copy, assign it to the parent. And lastly, copy, assign it to the parent, and I am allowed to modify anything in here because I have created it in my separate method. Therefore, the old root points to the same exact tree that you see with blue, and it points to these old S and T values, and the new one reuses most of that tree while only copying and changing the path that leads from the root to a given node. Another interesting feature of this vector is the slice operation. It's basically a sublist. How optimal can we make it? Also, Clojure avoids this and simply uses a wrapper around it, which makes it memory leaking just as ArrayList is. If we have a tree, this one with the alphabet, we want to store only on the middle part of it. A substring for some reason, let's pretend that we are writing a parser or a text editor or something. We want to keep only a smaller part of it. We have already seen with the edit that we can go down from the root, and when we try to calculate the index of the first element, whenever it's not the first of the arrays that it iterated down, we can simply ignore and null them out. Whenever we null out one of these nodes, then a whole subtree disappears, at least for the view of this root node. It will still be kept for the other one that we have copied. The same way we can check the index of the last one. we simply go down and edit and discard everything that is greater than it. We will end up with a tree that looks like this. Here we need an offset. Can someone tell me? Yeah, because you can read it. In constant time, effectively constant so-called, because it's required 2 times the height of the tree, which I said if it's not a base of 2, then it's a very small number. So in effectively constant time, we have a new root node, which is basically a new vector that represents only a smaller part of the array. We will get back to why that's important. Actually, now I will get back to why it's important. More advanced versions of this data structure make insert, delete, and merge also constant time. How that's possible? Well, here's a link. I'm not qualified to answer you that question. But why would it be important to insert anywhere in constant time? Why would it be important to not just slice, as in take a small part of it, but also merge it back? Imagine that you want a map operation, change every element one by one in a given vector. But in case you have billions or millions, maybe not billions because that won't fit in a memory, but millions of elements, you might want to parallelize that. If you slice it up in constant time, send it to different processes. Every process changes it, returns you back a new tree structure. If you can merge it in constant time again, then branching this way is basically for free and you can parallelize everything. Now that we know a few things about the algorithms that govern this data structure is working, let me tell you about a few things how I tried testing this and coming up with it. Since Javaslang already had a vector implementation, which was basically a persistent map with integer keys and object values. Therefore, it already had tests. So my normal approach of doing test-driven development, where I specify first what I want the interface to look like as a client, didn't really work. However, I managed to do a property-based testing on it. Since the number of states that this vector can be in is way too big, I cannot write test cases for every one of those separately. However, I can sample the input space randomly. If I choose, for example, in case of a slice, I choose the start and the end position randomly. Running that many times, I will get to a point where, for example, the start and the end will be in the same leaf, which might be a corner case. But this way of testing it and comparing the results against alternatives, you can imagine a simplified vector that is simply a huge array, and whenever you modify it, you simply copy everything and change a single element. It will be extremely inefficient, but very simple to implement. Therefore, you can compare the results against it. It's embarrassing how many mistakes were caught by this testing. I also tested, by the way, that whether the history is kept, whether I accidentally modified anything in the history previously. Since the algorithms that governed this data structure changed all over, I had code parts left that I thought were still used and code coverage told me they weren't. That part was also quite useful. Now let's see some actual benchmarks of how this data structure behaves. First, how did I measure it? As you have seen my failed attempt to show you that it was quicker, I was using JMH. It's a Java micro-benchmark harness which runs the same algorithm multiple times to warm up the virtual machine, after which it actually starts to measure the things once it's warmed up, once the optimizations are done. I found that instead of trying to avoid all the corner cases and trying to measure the relevant parts, I actually measured the sum of bulk operations. For example, if I wanted to see how quick a get operation will be, then I went through all the values one by one. I actually did it in a random order so that I'm not getting the values from the cache, but actually from iterating through the vector. I also compared it against alternative to see when I reached optimality, when it was good enough. I will show you examples immediately. For example, when slice ended up being 10 times faster than Scala, then I stopped. From that on, it was only getting more ugly. It was also interesting to see that performance doesn't compose. I optimized several methods independently, and then when I checked the big picture, it got a lot slower. It was also in very strange circumstances when, for example, I allocated a new array and started copying things into it with system array copy or something. If I introduced any value, even an if, even a even just a print line. Between these two, the JVM didn't optimize it. It zeroed out the array before. And lots of small details like this that you only see once you get your hands dirty and start optimizing these things. As I said about bulk operations, if you update one element one by one, it's difficult to compare it against a mutable alternative. However, even though it was a lot slower compared to a mutable array list, but we're not comparing the same thing. However, if we compare it against Java 8's stream API's map function, which changes all the elements one by one and returns a new value, which is actually the same thing as our vector does, our implementation turned out to be 2 to 3 times faster than that. It's probably because Java's stream API is lazy. How much memory does this thing consume? Testing it for 32,000 and 30,000 elements, so full trees of 1, 2, and 3 levels, we can see that I've compared it against normal Java's ArrayList, functional Java, P collections, Eclipse collections, persistent Clojure, and persistent Scala. Also, since I've said that primitives were also supported, I tried storing different types of primitives in it also. Storing 32 random integers in an ArrayList would occupy about 500 bytes. Doing the exact same wrapped types would require 540 bytes, almost the same as the ArrayList. However, if we take advantage and store the actual primitives, which won't only be faster, it will also make it a lot smaller. It will occupy only 200 bytes, and if we don't store ints but bytes, which wouldn't matter in case of an ArrayList, we would get about a fifth of the memory consumption. And for bigger numbers, that will go up even until 10 times less memory. How fast is it to access all the elements in a given array in a random order? I already explained why the random order is important for. In case of 10 elements, all the elements can be accessed 46 million times per second. Trust me when I say this won't probably be the bottleneck in your application. And if you think it is, benchmark first, measure, don't guess. Just because this might be 10 times or 5 times slower than accessing a simple array, it doesn't mean that your application will get that much slower. If we compare it against a get operation of immutable Java, we can see that it's about half or the fourth of the speed. If we, however, compare it to Clojure and Scala, even though our version is greatly simplified, we can see that it's mostly the same speed. Scala went so far as to write out every level. If this vector has 7 levels, then do this. If it has, no, 7, 6. If it has 5, if it has 4, writing out every possibility. Therefore, it had a bug in it for 6 years that it was never working for a given length because nobody could test it. It would have required so much memory. Our implementation is general, which means in some cases it might be somewhat slower. Let's see the speed of prepend, append, and of the bulk operation for those. Normally, as I said, that prepend and append were optimized because they're at the extremes of the data structure. Both Scala and Clojure tried to come up with something. In case of prepend, Clojure didn't, so we have to reconstruct everything. It's way slower than anything else in the list. However, in case of append, both are quite fast, even compared to a mutable Java version. And our version for inserting elements one by one is only about a third slower without all these optimizations. Again, the code is a lot simpler. However, we decided to optimize it in a different way by creating bulk operations. Instead of appending elements one by one, we provide an append all and a prepend all. These turn out to be, even compared to all the optimizations in Clojure and Scala, 4 to 1.6 times faster. What is the speed of an update? Compared to a simple mutable Java ArrayList or array, it's naturally a lot slower. However, it's not doing the same thing. One is version, the other is not. When we actually try to compare it against a Scala or Clojure, then we see our version, especially compared to the latest Scala, is about 2 times faster. And it's about the same speed as Clojure is. What is the ratio of slice? Java, P collections, and Clojure are all cheating in this way because they're only creating a wrapper. It's basically a memory leak. Whenever you try to get only a single character, that wrapper is actually storing the whole collection behind. Therefore, these comparisons are like apples to oranges. Still, it's only about a third slower than those implementations. And compared to Scala, which does it in a consistent way, it's actually 5 to 10 times faster than Scala. Our implementation of Vector is symmetric, meant for generic use, containing bulk operations instead of hacking the code and making it a lot more unmaintainable. And creating a new vector, for example, from array source is an order of magnitude faster than in Clojure. And also as in Scala, they haven't optimized that part. It has a very efficient map and filter operations. The map operation updates all the elements after a given function. A filter keeps all the elements where a given predicate returns true. Both of these are 2 times faster than Java's Stream API for ArrayList, which was a surprising find. It also has a very quick iteration compared, for example, against functional Java, is several hundred times faster iteration of one by one. This data structure is also optimized for memory. It provides a fast slice option, which is several times faster than the alternatives, which provide the same memory constraints. And since it has automatic support for primitive storage, it's also optimized for maintainability. For every decision, we have decided whether the small change in speed and memory are worth making this data structure less maintainable by other parties. Since this is an open source project, people come and go. Just because I implemented most of it, I might not be there to change everything. It was a lot more important to make it understandable than performant, and even in this case, we have achieved quite good results. Thank you.